Um, the experiment performed on Tuesday, October 29th, 2013 was Caffeine Extraction by Angelique De La Rosa. When we think of caffeine, we usually think of coffee or another dark-colored beverage, since caffeine is most commonly used as a stimulant to enhance one's mental alertness. Caffeine is actually a white granular powder, not brown. However, according to WebMD, caffeine is also used as a treatment for headaches and other medical problems such as asthma or ADHD. The purpose of this experiment was to extract the caffeine from the tea leaves, purify the extracted caffeine, and characterize the purified caffeine. To extract and purify the caffeine, 3 different techniques were used: solid liquid extraction, liquid extraction, and sublimation. 4 different chemicals were encountered in this experiment: caffeine, dichloromethane, sodium carbonate, and sodium sulfate. Caffeine was the compound that was extracted from the tea leaves. Dichloromethane was the chemical used to extract the caffeine from the aqueous layer after extracting caffeine from the tea leaves. Sodium carbonate was used to ensure that caffeine remained in its free base form. In other words, it acted as a buffer. And sodium sulfate was used to dry the extracted caffeine dichloromethane. The molar mass, properties, safety, and disposal of the chemicals are listed here. The first step of the experiment was to set up a heating mantle using a 100 milliliter round bottom flask and a hot plate to dissolve 1.1 grams of sodium carbonate. This was so that the sodium carbonate would react with any acids and with the tannins that may have been present in the tea leaves mixture by deprotonating them, thus turning the acids or tannins into salts, and that way they would remain in the aqueous layer during the extraction with dichloromethane. So first the sodium carbonate was dissolved, and then the tea leaves were added along with DI water, and then the water jacketed condenser was placed upright so that any vapors that would be released would flow right back into the mixture. So steam distillation could not be used because caffeine is a solid and has a very high boiling temperature. And if steam distillation had been used to extract the caffeine from the tea leaves, the only thing that would have been collected would have been water, because caffeine wouldn't have evaporated and traveled through the water jacketed condenser into the receiving flask. And that step is necessary to collect the distillate if we were to use steam distillation, and it wouldn't have worked with caffeine. Therefore, the water jacketed condenser had to be placed upright for solid liquid extraction to work. Once the tea leaves were boiled, they were separated from the aqueous layer of the caffeine mixture using vacuum filtration. The filter flask was used to collect the aqueous layer. The Hirsch funnel was used to separate tea leaves on the filter paper, and the strainer was used to try and separate as many tea leaves as possible so that they wouldn't clog the filter paper as much. The aqueous layer collected in the filter flask is what was needed for the liquid extraction. For the liquid extraction, the aqueous layer was added to a separatory funnel along with 2 milliliters of methylene chloride so that the caffeine, which is more soluble in dichloromethane or methylene chloride than it is in water, would be extracted with the dichloromethane, leaving behind the aqueous layer of water, sodium carbonate, and any other acids and tannins that may have been present from the tea leaves. So liquid extraction is used to separate an organic layer from an aqueous layer, since these 2 layers are immiscible and thus can be separated using only a separatory funnel and the collecting flask, or a separatory funnel and a Pasteur pipette, depending on which layer is to be collected. The centrifuge tube was used to break any emulsion that may have formed and to ease separating the caffeine dichloromethane from the aqueous layer. This was done 5 times to ensure that all the caffeine would be extracted along with dichloromethane. Once the extracts were collected, they were dried using sodium sulfate, and then the caffeine dichloromethane mixture was heated on the hot plate, and on the hot plate magnetic stirrer to evaporate the dichloromethane, since the dichloromethane has a really low boiling point. After the dichloromethane evaporated, crude caffeine was obtained. Another new technique that was used was sublimation. This technique was used to purify the crude caffeine. To do so, crushed ice was added to a centrifuge tube to create a really low temperature for the recrystallization of the caffeine to occur. And for the sublimation to occur, two conditions had to be satisfied: high heat, which was supplied by the Bunsen burner, and low pressure, which was supplied by the vacuum line. The pure caffeine was sublimed and then recrystallized on the outer tip of the centrifuge tube, and the impurities, which do not sublime under the same conditions as the pure caffeine, were left in the filter flask. And here is the pure caffeine obtained. To test for the purity of the caffeine, the melting point was measured using the mel-temp apparatus. Since caffeine easily sublimes, the capillary tube was flamed shut to allow for high pressure inside the capillary tube, thus not satisfying the two conditions for sublimation, and therefore the caffeine did not sublime. The caffeine was a white granular solid, but and it can be seen in this picture inside of the melting point apparatus, and once it was melted, it turned into a brown clear liquid, similar to the color of the mixture when the tea leaves were boiled. The mass of the tea leaves used to obtain caffeine was 1.93 grams. The mass of the crude caffeine obtained was 0.0297 grams, and the mass of the pure caffeine was 0.0107 grams. The melting point range for trial 1 was 223.4 to 236.2 degrees Celsius. And the range for the trial 2 was 221.6 to 234.2 degrees Celsius. And the average melting point for the two trials was 228.9 degrees Celsius. The mass of the crude caffeine per gram of tea leaves was calculated by dividing the mass of the crude caffeine by the mass of the tea leaves. And the amount of crude caffeine per gram of tea leaves was 0.0154 grams. The percent recovery for the sublimation process was calculated by dividing the final mass of pure caffeine by the initial mass of crude caffeine and multiplying it by 100. The percent recovery was 36.0%, and the percent error in melting point of purified caffeine was calculated by taking the absolute value of the experimental melting point temperature minus the theoretical melting point temperature, dividing that by the theoretical melting point, and then multiplying that by 100, and the percent error was 2.7%. The results were 0.0154 grams crude caffeine per gram of tea leaves, 36.0% recovery for the sublimation process, and 2.7% for the percent error in melting point for purified caffeine. The predicted H&MR spectrum for caffeine can be seen here. There were 3 CH3 groups, each attached to a nitrogen, and the nitrogen was part of a ring. The A peak corresponds to the CH3 group attached to the nitrogen, but it is the least deshielded because it is furthest away from the other 2 electronegative atoms, oxygens. The B peak corresponds to this CH3 group that is next to an oxygen atom, but it is not in between both of the C double bond O atoms. And the C peak corresponds to the CH3 group that is in between the 2 oxygen atoms, double bonded to a carbon as part of the ring. And the D peak corresponds to the CH group that is part of the ring and has a double bond and is attached to a C double bonded to a nitrogen, attached to a carbon double bonded to a nitrogen. The multiplicity for all of these peaks was S singlet, and the integration for the CH3 groups, the first 3 peaks, A, B, and C, was 3H, and the integration for the D peak was 1H. Time was an issue that was encountered during the separation of the tea leaves from the aqueous layer because although a strainer was used to separate as many of the tea leaves as possible, the filtration still took a very long time, and thus the student ran out of time and wasn't able to filter all of the boiled tea leaves, and therefore the amount of caffeine per gram of tea leaves was lower than it should have been. Another experimental error was that during sublimation, not all of the caffeine could be purified because there was some that was pulled by the vacuum towards the line, towards the opening where the vacuum was connected, and therefore that lowered the amount of pure caffeine recovered and the percent recovery. And the technique error of the student was that the student spilled some of the caffeine during the extraction, thus lowering the amount of crude and pure caffeine obtained. The techniques used to extract caffeine from tea leaves were different from the steam distillation technique that was used to extract eugenol from cloves. The caffeine had to be boiled, then extracted using the separatory funnel, dried, and then purified through sublimation. On the other hand, the eugenol was boiled just like caffeine was, however without the sodium carbonate, and it was also extracted from everything else in this same step by the steam distillation setup, whereas the caffeine was not extracted in one single step, but rather in two. Moreover, the cloves did not require sublimation to be purified like caffeine did. So, all in all, it can be said that the technique or techniques used to extract and purify a molecule are all dependent on the molecule's physical properties, such as the molecule's boiling point, solubility, and sublimation point of a molecule. The references used in this experiment are listed here.